Hello, this is Brian Washburn. I'd like to talk about linear momentum for a single and system of particles. We have defined linear momentum before. For a single particle, we use the symbol little p for the linear momentum. So what we can say is that the linear momentum p is defined as the mass times the velocity of the particle. What's important about linear momentum is when and when it's not conserved. Okay, and we can also relate momentum to Newton's second law. And so we know that what does a force do? A force causes an acceleration, but also by realizing that, well, acceleration is just the rate of change of the velocity. And if I assume that the mass of the particle does not change as a function of time, I can write this, but m times v is the momentum. And so I can write this as p dot. Okay, so what a net force does on a particle is changes its momentum. When is momentum conserved? So conservation momentum, well, it means that, okay, so conservation means that the vector quantity is a constant for all time. That must imply that p dot is equal to 0. And that only occurs from the equation above is when the external force acting, or the net force acting on a system of particle, is equal to 0. Okay, so momentum is conserved a constant only when the net force acting on a single particle is equal to 0. All right. Now what we want to do is look at momentum and conservation momentum for a system of particles. Before I do that, I'd like to introduce a notation because we have to sum over particles and we have to sum over their components. Okay, so let me talk about a notation for writing. I can write the momentum in the Cartesian coordinates, the x hat plus m y hat. Okay, times. So it's just right here plus p z hat. Okay. Now I'm going to define a new notation where I'm going to write the momentum as a sum over y is 1, 2, 3 of pi, and then I'm going to use the symbol ei hat. Okay. What does that mean? Well, P1, 2, 3 is x, y, z, so P1 is equal to x, P2 is equal to y, and P3 is equal to z. Okay, and then E1 hat. Now I just have to use some generic symbol. I can't put x, y, or z here, obviously. So that E is just some arbitrary direction, and that I'm going to define as the x hat, E2 y hat, and E3 z hat. Okay, so I'm going to use that notation there. People really don't like these e's. I'm not too sure. This is just some arbitrary direction. Okay, so now this is basically a sum over the components. Okay, and in fact, we get even more sloppy. Okay, let's get rid of this guy here. We can even get more sloppy. The way we can get more sloppy is by saying that P is equal to a sum. First of all, we just say sum over I, okay? And then we can write PI, a vector symbol there, okay? So we don't even, it's obviously that I is 1, 2, 3, and then PI vector is just the product of PI times EI hat. So P1 is x times x hat. Okay, well actually I should have wrote here, these are px, py, and pz. Those are the components. Okay, alright, so that's my notation. Alright, now what I want to do is I want to look at linear momentum for a system of particles. I'm going to define the net momentum. So what I have is I have a bunch of particles in space, okay, and I have to add up all those momentum. Okay, so what I'm going to do is the net momentum of the system particles is going to be the sum over alpha, where alpha denotes a particle from 1 to n, have n particles, finite number, and then I can write here little p alpha like this. Okay, so then this guy here is the alpha. That's a hard thing to say, particle, okay? And we sum over alpha, okay? Now, what are we going to show? Okay, well, we want to show under what condition is the net momentum of a system conserved, or when does it change? And what we're going to show is that the rate of change of the net momentum of a system is going to be non-zero as if there's a net external force acting on all the particles. Okay, that's what we're going to show in class. Now, how are we going to do that? Well, the way we're going to do that is we're going to first write down an expression for we're basically going to write down the net force acting on each particle. Okay, and so to go on, how do I write down the net force acting on a particle? So I can start off with, well, let's write down F. So this is the net force acting on particle alpha. Okay, and then what I can show is that, so there's two types of forces that act on alpha. Alpha is this particle here. There are the forces from all the other particles. Those are called internal forces. And the way I would write that is it's a sum of beta. Beta is so I have the beta-th particle here, and it acts on the alpha particle here. However, when I do that sum, again, beta is just an arbitrary thing, so I have to sum over all beta, where beta doesn't equal alpha, of the force of beta on alpha. And then, what other forces act on alpha? What's the sum? It's all the external forces acting on it. Okay. Now, you may not, so what does this mean? Well, beta cannot equal alpha, because that means alpha acts upon itself. So when I do this sum, I have to exclude, whenever I pick beta goes from 1 to n. Every time I do that sum, I cannot use a self force. All right. So then what do I want to do there? Well, I want to look at, so remember, this guy here. So again, what I want to do is I want to look at the sum of all the forces, okay, acting on that. And that's what I'm going to do, is use that result to show this right here. Now, the important thing about this is, notice that here I have a sum of internal forces, here I have a sum of external forces. Notice in this final result, which we'll drive in class, it's also in the book, there's no internal forces there. So what happened to the internal forces? Well, the internal forces are all going to add up to 0 because using Newton's third law. So again, to summarize that, the momentum of a system of particles will only change when the net external force on the system is equal to 0. I don't care what happens to the internal forces. Okay, that's the introduction. Now, again, this will be equal to 0 if the net external force acting on the system is equal to 0. That must mean that if that's true, then the system momentum is a constant with respect to time. So we're going to look at a problem dealing with that. Okay, so the problem we're going to look at is a rocket problem. Okay, so what I have is I have a rocket, and that rocket is flying in space, and there is it's not near a planet, so it experiences 0 net external force on the system. So since there's no net external force acting on the system, I can assume that the momentum of the system, okay, is going to be conserved. And that's how we're going to solve this problem. So let's take a look at the rocket as a function of time. So at some time t, the rocket is moving. It has a speed v, and the total mass of the rocket is m. All right. Then I want to look at another instant of time later. Okay, so then what happens is the rocket ejects some fuel. Okay, now, for notation, we're going to say that dm is actually going to be a negative number. Okay, that means that, but mass is always a positive number, so the amount of mass I actually produce is minus dm. This is just a choice, so this is the mass I eject. Okay, and then when I eject that, it has a velocity v exhaust. All right, then the rocket itself, its mass is now m plus dm. Remember, dm is a minus number, so this is a smaller number, so the rocket mass is going to be m plus dm, but that's going to be less than m. okay, because dm is actually a negative number. However, it speeds up. dv plus v is going to be bigger than v, so it has a little bit bigger v, and that occurs at time t plus delta t. Okay, so now we can write down, and remember what we're going to do, and we'll do this in class, is we assume that the rate of change of the momentum is equal to 0. That's going to be equal to the momentum at times t plus dt minus the system momentum. Remember, this is the system momentum at times t. Okay, so let's write down those terms. Just so the momentum at times t, let's just write that down. That's from the first diagram. It's just going to be m times v. Okay, the momentum at times t plus dt is going to be equal to, well, the momentum of the rocket, which is going to be m plus dm, times v plus dv. Now remember, here I have only one thing of the system. Here I have two things of the system, the little ejected fuel and then the rocket itself. And so then what I need to do is I need to include the mass of the fuel. Remember, dm is a negative number, so the mass is always positive. I need that minus sign there. And then the speed, it actually ejects in the fixed frame, is the speed minus the exhaust. Okay, so what I'm going to do is I'm going to take this equation here, subtract that, set equal to 0, and in the end I'm going to solve that. It's going to give me a first order differential equation. I'm going to solve for the velocity as a function of time, or I'm going to really, what I'm going to do is I'm going to really solve for the velocity as a function of mass of the object. Okay, so we're going to solve that, again, using conservation of momentum for a system of particles. Okay, so just again to summarize, we can define the linear momentum for a system as p times mv. The momentum of a single particle is only conserved if the net force acting on it is equal to 0. We came up with a notation for summing, where I can use this I notation. Again, we're just going to write I, and I is 1, 2, 3. For a system of particles, we have to sum up over all the particles, and we're going to use the term alpha for the alpha particle. Okay, and we sum from 1 to n. Normally, we're not going to write it that way. We'll show in class that the system momentum will change if an external force acts on it. And thus, for a system of particles, the momentum of a system of particles is only conserved if the net external force is equal to 0. And that is as a result of Newton's third law. Okay, we'll see you in class. Take care. Bye-bye.